Если я успею, то через неделю уже я дам определение, какие-нибудь примеры. Но если не успею, то самый крайний срок через 2 недели. Что определить тексты тоже.
Да, пошло, все хорошо. Сейчас посмотрим.
Что-нибудь.
Супер, все работает.
Okay. So I'm continuing this section about finite objects. Yeah, last time we discussed finitely generated objects. So today we're going to discuss finitely presented objects. So the definition is more or less the same as in the category of modules. So an object X is called finitely presented so for shortness I'm going to write FP. For finitely generated I'm writing FJ, here it will be FP. So if we have the following, so if first of all X is finitely generated and for any Y, another object, and epimorphism, so say Y, X, so this is epimorphism, say pi, the kernel of pi is finitely generated. So if you know the definition of finitely presented module, this is more or less the same definition. Okay, so the main result about finitely generated modules was the characterization of the definition in terms of preserving some special limits. Here we have a similar result, so let A be a locally finitely generated category so an object X is finitely presented if and only if we have the following. The canonical map, again I'm going to call this T sub X from the limit, so this is directed limit A X Y I to the A X limit yi. So if and only if this canonical map is an isomorphism, well, for any directed system of yi's. Okay. Do you still remember what the locally finitely generated category is?
The set of
Finitely generated generators. Yeah, just remember that in this section, this whole section, I assume that my category is the Grothendieck category. So, in particular, these limits make sense. Well, this limit for yi's. Okay. Proof. Let's go in one direction. So let's assume that, suppose T sub X is isomorphism. Well, of course, for any object X and, well, no, for X fixed and for any directed system yi. Okay. So let's consider a short exact sequence. Right, so where y is finitely generated. So the goal is to show that, so what we want to show in this proof is that k is finitely generated. So just choose any finitely generated y, any epimorphism, denote k the kernel. We want to show that the kernel is finitely generated, so more or less check the definition. Well, so let ki be the directed set of all finitely generated subobjects of K. Well, first of all, we know that the sum of Ki's is equal to K. How do we know this? Well, that was a condition equivalent to the condition that the category is locally finitely generated. It's equivalent way to say the same thing.
I'm sorry, how did we obtain that short exact sequence?
Well, just choose one, right? So we want to show that for any y which is finitely generated, any epimorphism, the kernel is finitely generated. So more or less, I'm just trying to check the definition that I give here.
So we assume some epimorphism and
Yeah.
assume its kernel.
So for any y, for any epimorphism of y to x, we want to show that the kernel is finitely generated. Okay, so this is, we know that because the category A is locally finitely generated. Okay, so then if you look at the short exact sequences, ki for some index I that sits inside, well, that is mapped to the y. Now we have a quotient y modulo ki. Well, we can take the limit, and a limit give us the following. We'll have y modulo ki is isomorphic to the y modulo the sum of ki's. Which is, by our previous observation, is, so this is y modulo the sum is the same thing as y modulo k, so this is isomorphic to the x. Okay. Now, well, there is a map G from x to the y modulo ki naught, such that the composition of the map G y modulo k y naught. So here we have q I naught x. So this composition is identity. So let me write this in terms of formula. So G q I naught is 1 on x. For this we use the same strategy as I used a week ago to show that there is such map G. So what's maybe important to notice here, so the idea is, of course, you just take this thing, right? So, well, this is with a fixed index, this thing for any index. Well, since this is x, right, and since we have this isomorphism, I use this for this family, so the identimorphism from x to the x can be lifted here. Now we know that any limit is a quotient of a direct sum of abelian groups. Using the fact that this is directed set, we can choose only one such G. But then, if you look at the short exact sequence,
Sorry, I understood. How do we obtain G?
I'll just explain how. Well, look at this formula, and for yi's, you use these things. So hence, on the right-hand side, you get the maps from x to the x. So here we have a distinguished element, the identity map. Hence, it can be lifted here, since we know that the limit So this direct limit is the quotient of direct sum modulo sum equivalence relation. We can lift it to finitely many maps. Now we use that this set is directed and choose just one map. This is the map G.
Okay, so we actually use a couple of times the fact that some things preserve the directness of the families we obtain, right?
No, we just use what we have in the statement of the theorem, this isomorphism. Okay, so observing that we have such map G is equivalent to saying that this short exact sequence splits, right? And if this thing splits, then we have a epimorphism from the y modulo k I naught to the k modulo k I naught, right? But what we can see from here, well, it is given to us that y is finitely generated, hence this quotient is finitely generated, this is also finitely generated, and we know that ki naught is finitely generated, so k is finitely generated. So now we can go in that direction. Which I'm going to separate in two steps. So on the first step, I want to show that, oh, let me again formulate what I want to show. So I want to show that T sub x is mono. So let's separate this into two steps. In the first step, this is mono. In the second step, we'll be showing that T sub x is an epimorphism. All right, so I'm going to need a diagram. So if you're taking notes, just leave space above this line and below this line. I'm going to add something later. So there is a map from x to the yi and from the yi to the limit. So let's call these canonical coprojections Q sub I. So if I want to show that this is mono, I want to assume that this composition is 0, right? So this map here that I consider has to be 0. I want to show that this is 0 in this limit. Okay, well, since this is 0, here I can embed the kernel of the Qi, right? And the fact that this whole composition is 0 means that I can factor this map through the kernel. But what do you know about the kernel of this projection? Well, there was a lemma that we proved maybe a month ago saying that this kernel is the sum over all j less or equal than I of the, well, actually the other way around, I less or equal than j of the kernel Fij. So now let's use that the limit between, well, of the Homs in the category A between x and the kernel of the Qi is isomorphic to the Homs between x and the direct sum of the Fij. Again, I is less or equal than j. Okay, this we know because we proved this for any finitely generated, x is finitely generated. So this is true, and this thing is the lemma that we proved a long time ago. Okay, so now I claim that I can.
Sorry, what did you prove long ago?
This is the isomorphism.
Fij is a map from y1 to yj, right?
Yeah, that's the map in the direct system, yes. Okay, so then I claim that I can find k, well, among such j, so this is at least I. Well, here notice that I have kernel of the Fik, right, sitting inside this kernel. Now, since I know, well, I can find I can find such a map such that the composition of the x to the
Не, можно на диаграмме сказать, где здесь I, а где здесь J? Я уже запуталась.
well, this is I. So this is Qi. This is the kernel of this map, kernel of this thing, and this is equal to the sum of J, which is at least I.
Спасибо большое.
Yeah, so now I have this map from the X to the kernel. So there is I can factor this map actually through the kernel of the Fik by this formula. So there is a case such that I can find such factorization. Oh, there is okay, I don't want to add anything to this. Okay, so but if this map X factors through the kernel, I can take the canonical, well, not the canonical, but the map Fik to the Y sub k. Well, here, of course, there is another map Qk. So now what we see, that if I go like this, I'll get 0. I'll get factorization like this, right? But if I go like this, I'll get again 0. So hence, this map from the x to the yi, this composition is a 0 map. But this exactly means that actually the map I consider is a 0 map. So this finishes the proof in one of the first claim that this is a mono.
I'm sorry, why didn't you have K? How it's defined?
Well, y sub k is given to us, right? We have this whole direct system. The problem is to choose the index k here, right? And I choose this k looking at this formula. So I have some map here. I can choose a k such that I have this factorization by this isomorphism.
Так, а там сумма ядер, да?
Yeah, thank you. This is the sum of the kernels of the Fij. I'm just applying this formula
Okay, you have
and for the finally generate object X.
But by this isomorphism you obtain something like I don't know, it's direct limit of some Boolean groups, like
Sure, but in this limit I have still an element which is just this element.
you mean it's just a union of all these things?
No, well, this is just the limit in the concrete category of abelian groups, so I think about this as I take the direct sum modulo some equivalence relation. So if I have element in the direct sum, this clearly give me an element in the limit.
So you have
Можно еще раз там заниматься здесь? Просто вот доказательстве, что вы говорите, я просто не поняла, что произошло.
Я не понимаю пока вопрос.
Хорошо, можно просто еще раз доказательство, пожалуйста?
Well, the proof is the following. I have a map from the x to the limit, right? Such that this whole composition is 0.
Какая композиция?
Well, from x to the limit, this is 0. I want to show that this is a mono. So I'm assuming that I have something, right, some map, which is sent to the 0. And of course, this map T sub x, what it's doing is taking a map from x to the y I and just compose this with the canonical coprojection. That's what I consider in that diagram. Take a map, right? Take a composition with canonical coprojection and assume that this composition is 0. Then I want to show that this map, well, maybe this is not actually 0, but in the limit this is equivalent to 0. And this equivalent to 0 exactly saying that I can find another y sub k such that this composition is 0. This is what I'm trying to prove here. And the proof is the following. If I know that this is 0, well, clearly just by definition of the kernel, this map factors through the kernel. Now for the kernel I have this description. Now looking at this formula, I can say that this map actually factors through some map for the object kernel Fik, right? But now, if I just look at this whole composition from the x to this kernel, which is the same thing as this map, both triangles are commutative, so this whole map from the x is 0 to the yk. So this means that this map is 0, which means that this map is equivalent to a 0 map. So this is a monomorphism. Okay, so the second step, T sub x is an epimorphism. Again, want to show. Well, let's fix a map. So let's say f is a map from the x to the limit. Right? I want to kind of leave this map to this part of the formula, to the left hand side. Okay, so this is f. Let me just introduce some notation. So y prime with the index I, by definition, is the image of the q sub I. And then we know that the limit, direct limit of yi's is the sum of yi's prime. That was a lemma that we proved, again, a long time ago, but in the beginning of the discussion of the abelian categories. Now, again, I need some diagram. So the first part is the following. I have yi. Again, I'm going to kind of add something above this line. Canonical coprojection. Canonical map from the object, from the object to the limit. So I have yi. This is maps to the yi prime. Well, I have some kernel. Let me call this k, the kernel of this map. Now, of course, here I have a canonical map to the limit. Now, essentially what I'm saying is that this composition is just the map qi. Just another way to present this map. All right, so now here I have an induced map from the x. Let's call this f prime. Right? So I'm just kind of factoring the map that is given to me through the image. Okay, so for this two maps, yi and x, I can form a pullback. So let's call this object P for shortness, but this diagram is a pullback. PB is representing this.
Why this map actually exists from x to y, I prime, f prime?
Well, you have this given map from the x to this thing, right? Which is just the sum of these objects.
Okay.
Well, you kind of just restrict this to one of the summons. And you'll get this map. So this whole composition is just the map F.
Oh, but from do we have like in general the operation restriction in the categories here theory, or like we can't really call this like can we just restrict some maps and obtain some new maps? Is it a legit operation?
I think this is much easier than what you're saying, that because here, well, I have definitely, well, I have a map F, right, from the X to the sum. Now, so now I have y prime I that sits here, right? So we have a canonical map, and I guess what I really want, I want to map in the other direction. So I want to map like this, and then I just take the composition.
Yeah, but what is this map?
Well, you take the image of the, well, what was this thing? It's just the image of the x, of the what? Of the y I prime, right? You take the coproduct and map this, well, say to the limit, since we don't fix any other notation, right? So
But that's just this sum, right?
yeah, so this will be this sum. Now okay, so here we have the this thing. Now I want to understand how I get from this image a map to the y I prime. Well, again, I think it's a little bit easier than what I'm trying to do here. There's nothing complicated about this map. It's just more or less the combination of couple of definitions. So let me just maybe try again. So I have a map F, which is a map from the X to the sum. Right? Now, inside this symbol, this is well, let me try again. So if this is the limit, so from the limit I have canonical maps, right? So the maps from the, well, in this direction, right? Now, yeah, but wait a second. If I just want this map to the limit, I'll get this map here, right? Because any map to the limit is completely determined by its component, so this is just the component.
But this is a quote.
Yeah, so hence the map in this direction. I mean projection in this direction. Well,
Wait. So I think you need the opposite arrow.
yeah, yeah, that might be correct. If I want the map from the limit, right, then this is determined by the, yeah, but now I have map to the limit. Well, anyway, so this doesn't work. Okay, yeah, so I have a map to this sum now. Well, I can take projection. So the question is why I can take projection, and this map will be just the composition with the projection. Well, maybe we just here. No, we have a map from the x to the limit, so that this direction is correct.
Сейчас мы доказываем.
I'm taking any map f. I want to leave this map from the right hand side to the left hand side.
Yeah, we're proving subjectivity.
So I think the direction of this arrow is definitely correct.
Yes.
Yeah. So, but going back to this thing, how I can construct this map? Well, again, let's use the definition of the colimit, but now correctly. I want a map from the colimit to this thing. So now I need to specify what this map is doing on each of these yi's, right? But this I can do, because if the index, let's say this is j, if the j is equal to I, no, I have this map. This is the map. And if the index is not equal to I, any other index, this will be by definition zero map. Hence, we have this map. And the map I want to...
But there you want to put primes maybe somewhere, no?
Primes?
Oh, no, sorry.
Yeah, I think it's okay. So the point is that from this limit, I have all the maps for all these things. For if the index j is equal to I, this is this map. And for all other indices, this is just a zero map. As I promised, this is just a combination of two definitions. Okay, so this whole composition of two maps is what I want to call f prime. Okay, so then I want to take a pullback and call the result of the taking pullback as some object p. Well, by the lemma 1 from the diagram lemmas, I know that this map from p to the x will be an epimorphism. Now, and again, by the lemma, I think again by lemma 1, I can claim that there is an isomorphism for the kernels. So here I need the following observation. So I want to say that there is object p prime sitting inside p such that p prime is finitely generated, and the composition of the two maps is an epimorphism. So in other words, if you have a finitely generated object, in this case object x, you have an epimorphism from any other object. Inside this object you can find a sub-object which is finitely generated, and when you stick to this sub-object you still get an epimorphism. This will be a lemma, so let's think about this as a lemma. We're going to do this on the seminar. Just general property of finitely generated objects in any category. So by this I can add this p prime here and take another pullback, which in this case will be intersection of the k and p prime. So this is some sub-objects. Now, again, using lemma 1, the co-kernels are isomorphic. And we get the following diagram. Okay. So now what we can notice here that k intersect with the p prime is finitely generated. Okay, and since this is finitely generated, we're using the same logic as before. We can choose index k such that the map from the k intersect with the p prime to the kernel of the yi to the yk. Well, this sits in the kernel of this thing. So again, by choosing this index k, I'll get a map here to the y sub k. So this is fik. And now, if I just look, of course here we still have the same map, q sub k. Okay. So now we look at this map from the p prime to the yk. When restricted to this object, we will get 0. Right? This means that actually this map lives on the co-kernel, on the x, which we can identify with this x. So we constructed the map from this x to the yk, such that, well, of course, everything is commutative by construction, but if I look at this composition from the x to the yk with the canonical projection, I'll get the map that is given to me. And this finishes the proof. Okay. If you have questions, ask the questions. If you don't.
How did we obtain YK?
Well, it's just the same logic. So this is finally generated object, right?
Yeah.
So this finally generated object. Now, this by construction is a sub-object in the kernel, right? So it means that if I now this kernel k, well, previously I can identify this with the kernel qi, right? This is the same sum, hence there is a factorization. Well, this is the same as before. There is a factorization through some yk. Or maybe it's better if I add the index here, but it's a little bit heavy annotation. Okay. So next theorem.
Now, remember that can we just, like, maybe can we say that just easily with the using the definition of finitely generated object, like, because we had something like there exists some index from the family that such that it just equal to the x, like I0 or something like that.
Yeah, but you need a statement like this. And for this, you need to know that the object here is finitely generated. And that proves the object is intersection of ki with the p prime. Yeah, so the next theorem, I'm not going to assume that I have a growth in the category, but I have more detailed assumptions. So A is an AB3 star I have doubts about the star, so let me address this later. Category with finitely presented projective generator. For shortness, people just say pro generator, but this is precisely projective generator. So let's say that R is the endomorphism ring in the category A for this projective generator, pro-generator. And then the functor H sub P from the A to the right modules is exact equivalence of categories. Now, first of all, it's clear that H sub P is exact and faithful. Right? It's exact because the object is projective, and it's faithful because the object is generator. Just a combination of two definitions. Now let's take an object n. So object in the category A. And with this object, I want to associate two functors. So one functor I'm going to call f. So f is just a functor co-represented by n. And the functor g, and this is home in the category of the right R modules of the h sub p of the n. So these are two definitions of two functors. So what I want to achieve, I want to show that this thing is an equivalence of categories, right? So I know exact equivalence, exactness I already know for free. I don't have to prove anything. Faithfulness also comes for free because I have a generator. I want to show that this is full, and I want to show this is essentially surjective. So showing that this is full is actually showing that these two functors are isomorphic, f and g, for any object n. So I think in the proper notation I need to say that this f depends on n, this g depends on n, but I want to have used notation and use the shorter notation for two functors. Okay. So I want to show that the g of m is isomorphic to the f of m, and this is true for any object m. Well, the first observation is that when m is equal to p, this is clearly true, right? You compute this functor f on the object p. So what you get here is just the hp of n, right? So f of p is h sub p of n. And the g of p, well, if you plug in p here, you'll get just the ring R. Home over R from the ring R to this module is precisely the same module, h sub p of n. So they are isomorphic. Hence, I'll get the following. For any set I. And so this is a coproduct, right? So it means that actually what I need in this theorem is co-completeness, which is AB3. This is why I had doubts about this star, right? So this is where I use AB3. No, I use the previous observation, and why this coproduct exists, because I have AB3. Okay, now let's go to the general object M. For an object, I can choose a presentation. Right? Since P is the generator, I have a surjective map like this for some set I. Right? So this map has some kernel. I just repeat the procedure for the kernel and take the composition. So this will be. Is it clear? Do I need to explain this? Well, the idea is this you know, this is equivalent to the definition. Now suppose we have some kernel K, right? And then for kernel K, I can find another set J such that here I have epimorphism. Just take the composition. Okay, so any object has such presentation. So now let's apply f to this presentation. Notice that the functors f and g are contravariant functors. So then I'll get f of m, and this is mapped to the f of the p to the I, f to the p of the p to the j. contravariant and also left exact. So hence this is exact. Now I also have the same thing for the second functor g. It's exact by the same reason. So here, of course, we have an isomorphisms that we already know. So if you look at the canonical map here, I claim that this is also an isomorphism. No, let's just pause for a second. If I know that this map is an isomorphism, if I just look at the definitions of the two functors f and g, I can say that functor h sub p is full. I know that it's faithful, and it's also full. So you only need to show that actually this thing is an isomorphism, but that's a very elementary observation. Notice that here all the things are actually abelian groups, and this is just isomorphism for abelian groups. So we can do something like diagram chase, right? So suppose for this map there is some element which is mapped to the 0 by this arrow, right? We can consider this element here. This is mapped, well, by the isomorphism to an element here. So if this goes to 0, so this composition sends this element to 0, so this composition also has to send this to 0, but that's not possible. This is embedding this isomorphism. So there is no kernel. Now let's show that this is a surjective map of abelian groups. Take an element here, right? So we can consider this as an element here, since this is just by the exactness. Well, and also notice that, take x, this x is mapped to some x prime, and this x prime maps to 0 by the exactness, right? So take this x prime, we can uniquely leave this here, and again, by the commutativity of the second square, this is mapped to 0. Hence, it actually comes from some element here. So this diagram chase shows that this is an isomorphism. So the functor h sub p is full. So the last step, I want to show this is essentially surjective. Well, I know that for any module, well, in the category of modules, R is a projective generator. So just repeat the previous presentation argument and can say that for any module, there are sets I and j such that, let's give this module name T, such that T has a presentation like this. So let's call this presentation map phi. Okay? We want to show that the functor is essentially surjective. So for this, I start with any object, choose a presentation for this object, but now this phi, this is in the home over R. Well, now the R to the J, R to the I. But I can also say that this is the same thing as the home in the category A of the E to the J, E to the I, right? This is by the fact that this is fully faithful functor. Right? If I start with such home, apply h sub p to this thing, I'll get exactly this. So this has to be an isomorphism because this thing is fully faithful. But it means that for this phi, there is the corresponding psi that corresponds to phi under this isomorphism, such that if I consider yeah.
Because f and j are contravariant, so yeah, because they're both contravariant.
What? Well, the functor HP is covariant more or less by definition.
Yes.
This is the home where first argument is fixed, and then the second argument home is covariant. So, but actually we finished the proof, right? I start with any object, choose a presentation, take this presentation, presenting morphism, find the corresponding morphism in the category A, take the co-kernel of this thing. Now if I apply H sub P to this thing, I'll get exactly this diagram. This is a presentation of a module. The same logic as before. You take an object, since you have a generator, you have an epimorphism from some power of the generator to the object. It has some kernel, do the same procedure to the kernel, and then combine these two maps together. So in this case, this is just in the category of right R modules, and the generator is just R. Okay, next theorem is based on this.
Why do we have the equivalence of categories?
Well, what's an equivalence? We proved in the very beginning of the course the theorem that we have an equivalence of two categories if there is functor which is fully faithful and essentially surjective. We check these two conditions here. So theorem, well, I want to call this Morita equivalence. The following are equivalent, and any of these three conditions is called Morita equivalence between two rings. So, let's say that R and S are rings, then the following are equivalent for the two rings. First, the category of the right modules are equivalent. 2, ring R is isomorphic to the endomorphism ring over S of some progenerator P. So P is finitely presented progenerator. And 3, there is RS bimodule T such that the tensor product with this T give an equivalence of categories from the right modules over R to the right modules over S. So these three conditions are equivalent, and whenever you have one of these conditions, you say that the rings R and S are Morita equivalent. So in other words, if you're interested in the representation theory, well, you can say that the representation theory of two rings are equivalent, but of course the rings don't have to be isomorphic. We're going to see examples later after the proof. Okay, the proof is actually much easier than what we've done today before. So let's show that 1 implies 2. Well, we have some equivalence of categories. So let's call this equivalence phi. So this is an equivalence of categories. Well, then just take P to be phi applied to R. Right? Well, I think it's clear that P is a finitely presented projective generator. Well, because this is completely categorical conditions, being projective, being finitely presented, and being generator. So if R satisfies these conditions in one category and the two categories are equivalent, P has to satisfy the same three conditions. So that's a finitely presented progenerator. Well, we only need to understand why the endomorphisms of this P are the same as R, but this is again very easy. Oh, this is just ohms over S from the P to the P. I can write this phi of R. Now use that phi is fully faithful and write this as a ohm over R, and R, which is R. So with this, why 1 implies 2. Now 2 implies 3. Well, here we need a previous theorem, right? Because here we have a ring S. In this, in the category of the right S modules, we have this finitely presented progenerator. Hence, the construction of the previous theorem tell us that we have an equivalence. Right? So the H sub P give me an equivalence from the modules of the over S to the modules over R. So this is the hard part of this theorem, but we proved this exactly before this theorem. So what's the bimodule that we consider here, right? So notice that the bimodule give me an equivalence going in the other direction. But if this is an equivalence, the left adjoint also give me an equivalence. But the left adjoint is exactly the tensor product with P. And of course, notice that the P is precisely an RS bimodule in this case. Right? Well, because P is a module over S, it is given to us, right? But any module, well, anything, any abelian group is a module over its endomorphism ring. Hence, this is module over S on the right and over R on the left. Yeah, and finally,
So T is P.
yep, in this case, T is the same thing as P. Just notice, we need to notice that P actually is a bimodule. Now, 3 implies 1. This doesn't require any proof. Right? We know that we have, well, I think I said this, but it's not on the blackboard. So there is an RS bimodule T such that this functor tensor product with T is an equivalence. So if this is an equivalence, well, we just forget part of the data and say this is an equivalence. Okay. So we can do the following. So example, consider A to be the category, say, of the right R modules, and as a generator, take R to the n. So then, if you look at the second part,
And what is that?
well, n natural number. Notice this has to be a finite number, otherwise this object won't be finitely presented. And of course this is projective, this is a free module. And of course this is a generator, because even R is a generator. So if you add something to the generator, it's still a generator. But if you just look at the condition 2, you get the following. Well, so let's say, well, maybe to be, well, to use the same notation as in the theorem, let's call this S, and this is also S to the n. Right, so then R is just the matrices of the size n by n with coefficients in S. And hence we get the equivalence of categories. Modules over S are equivalent to the modules over the matrices of the size n by n over S. So these are example of two Morita equivalent rings, but they are not isomorphic as rings, of course.
Как еще раз такое называется?
No, it's here, Morita equivalence.
Ну, понятно, что это были...
And so finally we were able to solve the problem from the first quiz.
Well, with this technique, it's not really a problem. Yeah, so that's what an example and a remark. So if R and S are commutative rings, suppose they are Morita equivalent, so modulus over R is equivalent to the modulus over S, then R is isomorphic to S as a ring. So in the commutative situation, we can't have this not two isomorphic but Morita equivalent rings. Can you see how we can prove this?
Yeah, I think just look at the image of the isomorphism of the ring.
Okay, so you can do this, and you get, if you start this one ring, you get some projective generator in general. Why do you think that this is the ring S?
Is it true that projective generator is unique up to isomorphism?
No. As just mentioned several minutes ago, if you take a generator, add something to the generator, it's still a generator. Well, the question is again about quiz 1. You take these two categories and compute the centers of these two categories. So the center of such category is the center of the ring. So because this implies that the center of R is isomorphic to the center of S. And if the rings are commutative, this is just R and this is just S. Okay, so the last section in this chapter Mitchell-Fried embedding theorem. Now I want to start with the weak version. And actually, this is the only thing I'm going to prove. For the general version, it's not really hard, but actually this requires, I think, 1.5, maybe 2 lectures of other techniques, and I just don't want to do this because we won't have time for homological algebra. So I want to prove this weak version and then kind of give you several steps how you can do a general version. Okay, so let B and an A, B, 3 category. With projective progenerator, for shortness, with progenerator P. Any small exact subcategory A of B has an exact fully faithful embedding to the right modules over some ring R. So for some ring R. So why this is a weak version? Well, because you have two assumptions. You assume that the category B is AB3, and you assume that you have this projective generator. So the general version stays exactly the same, but without these two assumptions. You take any abelian category, for any small subcategory, you can find the ring and this embedding. Okay.
Wait, so any abelian category is AB3?
No. That's not true.
So we just,
To conclude that for any small subcategory A, you can construct such an embedding, you don't really need this assumption AB3 and progenerator. You can remove this from the theorem. And that would be the general version of the Mitchell-Freight embedding theorem.
We just assume the same, but without B. For any
AB3 and
Without AB3 and existence of a progenerator.
So in fact, we're just proving it for a smaller amount of categories, right?
Yeah. Well, in fact, this is kind of a step in the proving of the general theorem. You prove this thing, and then you construct another category such that you can, with these two properties, such that you can exactly embed your category in this category with these two properties. That's the strategy. So here, I want to introduce another progenerator specifically for this subcategory A. So this will be a direct sum or coproduct over the all objects in the A. So this is a set. So this makes sense. And I take P to the power of the set, which is just the maps in the category A from the P to the X. So this is a progenerator. And the ring R is just the endomorphism ring in the category B of this progenerator. Of course, the embedding that I want to consider is just H sub Q. So that's a map from the A to the right R modules. Okay, so what we already know as before, we know that this thing is exact and faithful. Well, by the assumption, because P is a progenerator, hence Q is a progenerator. And progenerator exactly means that this functor is exact. This is a property being projective. And faithful, this is a property being generator. Okay, so the goal of this proof is to show that H sub Q is full. Right? If I have this, I can say that I proved everything that I claimed. Okay. Let's start with two objects X and Y. So let say these maps are alpha and beta. And the second map, well, for the second map I don't need the kernel. So I choose two objects X and Y. I can cover them by this progenerator Q. So these X and Y are objects in the category A. So these maps exist by construction of the Q. Well, in this case, I denote the kernel by K, and in this case, I don't need the kernel, so no notation for the kernel. So then I have the following diagram. I take the short exact sequence, I apply functor H sub Q to the short exact sequence. So that's an exact functor, so I still get a short exact sequence. So the induced maps I'm going to call alpha with the lower star and beta with the lower star. Okay, so suppose I have some map phi to the h lower q y. Right, so if I want to show that this is full, I want to show that this map phi is actually induced by some map from the x to the y. Okay, well, here I also have R, also have map pi lower star, and this is still an epimorphism. Well, first of all, I can find a lift of this phi to the R, so let's call this psi star. Well, how we can do this? Well, this is just a ring, and the map from a ring to anything is very easy to define. It's completely determined where it sends 1. So here, element 1 is sent by this composition to something. So take 1, apply beta lower star to this 1, apply phi to this beta lower star. I'll build an element here. So this map is an epimorphism. Hence, I can just choose some lift of this element in the ring R and determine that the psi lower star on 1, well, it's just some element of psi lower star of 1, just some element such that if I apply pi lower star to this element, I'll get what I have. So this is completely determines the map psi lower star. Okay, now
Тогда нужно, чтобы изменилочка была с реакцией. Почему не с реакцией?
this is because the functor, so I'm getting this thing by applying functor h sub q, and it preserves the exactness. So this is exact, this is exact. Hence they have epimorphism. Okay, so let's go back to the diagram in the category A. So here I have alpha, q, beta, x. Phi. So first of all, I claim that this map, I know that I can leave this as a map from the Q to the Q. Right, because essentially this is just an element in the ring, an element in the ring, well, it's just a map from Q to the Q by the definition of R. Hence, there is a map here. Psi. Now, if I look at the composition of the pi, psi, and alpha, so going like this. What is this map? Well, I claim that this map is actually 0. No, just a lift of this map to the object Q. This is possible because R is precisely all the maps from Q to the Q, and this thing is more or less the same thing as an element in the ring R. Yeah, but I claim that this composition of these 3 maps is 0. Do you see why the composition is 0? No. Well, what if I add stars everywhere for these 3 maps? Then I'll get 0, right? So this thing is 0. Because I can as well go like this, which is 0, since this is exact. Then apply some maps, it's still 0. But a functor h sub q is faithful, right? So pi lower star c lower star alpha lower star is 0 and h sub q is faithful. Hence this map is 0. Okay, so this composition is 0. Now let's look at the following diagram. We have maps in the category A from the x to the y. Now I have composition with beta, so this is beta upper star A Q Y A. This is composition with alpha, alpha upper star A K Y. Okay, so I can obtain this if I just look at the short exact sequence, and now I apply functor where the second argument is fixed and this is y, and this again is the short exact sequence. I don't know about the exactness here because I don't know any properties of y. Okay. Now here a map from the q to the y. So the map is the composition of the pi and psi. And if I take the composition with alpha, I'll get this map, which is 0. So this is sent to the 0. Hence, this composition of the pi and psi is actually coming from some map psi. And the psi is sent to the, well, this is supposed to be composition with the beta. So psi composition with beta, which is this thing. Okay, so this is by the exactness of this sequence. So I take an element, this element is mapped to 0, hence it comes from the element, some element here, I call this psi. So psi is mapped to the composition of psi and beta, which is P and C. Okay, so the claim is that the phi is actually psi lower star. So this follows immediately from another short exact sequence. 0 home over R, h sub q of x, h sub q of y, home over R, R h sub q of y, and finally home over R, h sub q k, h sub q of y. The logic is the same. You look at the short exact sequence and then take the home with h sub q of y. So this is exact. Now here in the kernel I have two maps. I have psi and I have this is psi lower star and phi. Now these two maps are sent, well, on one, if I start with phi, I will send phi to the composition with the beta lower star. I know that this is the same thing as the pi lower star, c lower star, but this is by construction the same as psi lower star, beta lower star. The end of the proof. Okay. So I think I have just several minutes. I want to say maybe just.
Который там после вписывают это все, правда?
Yep, that is correct. Okay. So remark. For general version of the embedding theorem, well, you need to prove several other things. Well, first of all, you consider left exact functors from the A to the abelian groups. And well, by definition, this sits inside all functors. So let me call these modules, say A modules. So this is the embedding. Well, this embedding actually have a left adjoint. Let's call this L. So L is left adjoint to the embedding. And then you prove several properties. Well, maybe I formulate this as one of the properties. So first, Lex AAB is abelian, which is already a non-trivial property. If you try to do this directly without any techniques, it's not so easy to show. 2, there is L, which is a functor like this, such that L is left adjoint to the embedding functor. And this L satisfies several properties. So such that L, well, not such that, but there is a left adjoint, and L is exact. The composition of the L and I is the identity. Probably all I want to say. So other observation would be 3 Lex A AB is complete, which is easy, right? You need to show that they have products, but the products of left exact functors are left exact. That is because the kernels commute with products because both are limits. So this is easy. For Lex has a generator. Well, this is also a very simple statement. You just take the product of the H lower X, where X are all objects in the skeleton of A. So this is the generator. 5. It's not so easy to show that the Lex has enough injectives well, in fact, Lex is also co-complete. And the co-completeness is less trivial, but still quite easy if you just look at this functor L and kind of induce the co-completeness from the co-completeness of the all modules over the category by using this identity. It's an easy exercise. I'm not going to do this. So this is complete co-complete category. It has enough injectives. Automatically, we'll get 7 that the Lex has injective cogenerator. This is for free. So then we look at the unit embedding from the opposite category of A to the Lex. Or just the unit embedding, the standard unit embedding. Well, then you can as well consider the same unit embedding as a map from the A to the legs A, AB, opposite. That's the same functor. But now, in the legs, well, we have completeness, co-completeness, and we have an injective co-generator. Hence, here we have a progenerator. So, if we can show that this is exact, then we're done. So this is the 8 steps you need to do if you want to prove this general theorem. Well, I think the 1 and 2 are hard, 4 and 3 are trivial, 5 is hard, this is trivial, well, easy exercise, automatic, and more or less easy exercise. So this is the end of today's lecture.
Здравствуйте, можно вопрос задать? Мы тут, правда, на месяц остались, вот, возник вопрос по этим, значит, повторным пределам. Вот, там вопрос такой вот. Вы говорили только про повторный предел, что они равны, где существуют.
Да.
Вот. А есть же еще предел функтора, который из произведения категории идет. Вот.
Да.
Вот. Мы поняли, что если повторно существует, он равен. Вот.
Да.
А вот в обратную сторону это
Если
непонятно.
повторно существует, то он будет существовать и будет совпадать. Либо, если повторно, то будет из обычной категории, из производной категории. Он произвел будет, он будет.
Да, и он будет равен.
Ну, это правда, вы можете взять по, как бы, по произведению категорий, по, как бы, по одной категории, по другой категории, в другом порядке. И это все 3 штуки дают один и тот же ответ.
Даже если вот условие начальное, что существует предел произведения.
Вы хотите, нет, это предположение, что все пределы, которые написаны, существуют. То есть это как бы, допустим, 2 категории маленькие, у меня категория, например, там полная, да, все малые пределы существуют. Тогда да. А если там существует только по какой-то причине, я не понимаю, почему, если у вас есть произведение. То есть хотите сказать, что у вас, в принципе, будет такая диаграмма, произведение 2 диаграмм, для которой существует, а для отдельно. Это вполне, я думаю, возможно.
Возможно.
Да, то есть я не вижу здесь противоречия ни с какими теоремами.
С термофобией. Потому что там в обратную сторону, там если существует интеграл произведения, то существует повторный интеграл,
Очень
ему
равно
равны.
то, что можно принять теорему Сметана в теории категории, типа, это даст какие-то решения. Ну, правильно, почему я имею в виду.
Мы знали, что интеграл есть в теории категории, да, там эти end и equent.
Да.
Да. Вы про это не будете рассказывать?
Нет, я про это не буду рассказывать. Если про это хотел рассказать, я про это рассказывал еще во 2 главе, а я уже 3 закончил.
Да, вы разбирали этот midterm?
Если в классе решения не было такого,
Просто можно как-то понять, как это вообще решается.
то вы можете у кого угодно спросить. Я думаю, здесь почти все это решили.
Почти все это решили. Я спрашивал, типа, есть ли здесь те, кто это решил? Никто не ответил.
Но не стесняются просто. Ну, вот, например, Миша Зайцев все решил. У него 100 баллов из 100.
Один человек нашел из 5. А вот в листочке там задача про калим-лим и лим-калим. Ну, в смысле, что там нужно... Если
В смысле коммутация там конечного и этого самого такого специального вида.
Да, вот что это за категория специального вида, вообще, что это за свойства такие?
Ну, это типа такое обобщение на направленных множеств, на ту ситуацию, когда у вас не просто множество, а действительно есть как бы много морфизмов между объектами.
То есть не обязательно один.
Не обязательно один, да. То есть если вы в том определении положите, что у вас как бы не больше одного морфизма между 2 объектами, то вы получите определение направленного множества.
А здесь просто много морфизмов быть, но нужно, чтобы они уравнивались еще.
Да. Вот такой как бы Да, там, я помню, ты спрашивал такую же задачу, что вот если у вас есть, существует при себе предел по таким категориям, то это то же самое, что существует предел по направленному множеству.
Да.
Вот это вот интересное, нетривиальное утверждение. Понятно,
Так это вы доказывали, по-моему.
Нет, я это точно не могу доказывать, потому что это не то, что просто доказать, я это запомнил. То есть вам каким-то образом нужно что сделать? Вам нужно догадаться, как по вот этой категории такой специальной построить подходящее направленное множество, которое дает такой же предел. И это не то, чтобы очень просто.
Там... вы брали в случае этих сетсов, там, направленное множество под множество, по-моему. Да?
Ну, это все равно не то, про что я сейчас говорю.
Не то, да.
Просто вот эти все категории с такими свойствами, они очень удобны, потому что на практике, то есть с теоретической точки зрения, это как бы свойство известное, да, понятно, это существование всех направленных там, пределов, легко пределов, а на практике это гораздо более удобно.
В смысле, не пользоваться предпорядками, а пользоваться такими категориями?
Да, потому что их проще обнаружить просто. Например, там можно взять, доказать, что какой-нибудь произвольный модуль, это будет предел, копредел по такой категории, как там написано, конечно, представленных.
Такой
Категория будет
мне кажется,
всех конечно, представленных под модулей данного модуля. А если вы возьмете исходный модуль плоским, то там, если вы это утверждение доказали про модули, возьмете модуль плоским, то у вас почти автоматически получится, что плоский модуль – это предел по такой категории этих самых
свободных.
Свободных, да. Теорема Говорова, Лазера.
По-моему, не автоматически, там просто... Ну, я вот читал этого Эйзенбада, там очень сложное доказательство, переформулировку того, что модуль плоский в терминах там соотношений. Вот, и из этого...
как бы для меня это автоматически. Потому что свойства плоских модулей надо знать.
Что такое плоский модуль?
Тензор умножения него точно функция.
Ну, это просто на самом деле одно из эквивалентных определений, такое свойство, что если у вас есть морфизм бесконечно представленный в плоский, он обязательно пропускается через свободный. Это утверждение эквивалентно определению плоскостности.
Надо учить.
Надо, мало того, что учить надо каким-то, просто понимать, какие вещи надо учить, чтобы их учить.
Ну вот теперь понимаю.
Плоский модуль.
Не, ну это база. А вот еще вопрос. Там вторая задача.
Не, я по номерам точно ничего не помню.
Ну, в общем, продукт, в общем, эти произведения существуют тогда, когда копроизведение существует, и категория маленькая. Вот. И
Одна из
как решать?
моя любимая задача практически. Вот
Да.
такой неожиданный как бы результат.
очень. Да. И сейчас. Что-то я хотел сказать. Там есть теорема Фройда, что...
Фрейда.
Или Фрейда.
Точно помню, что Фрейда. Фрейда Маклейна. Что-то такое.
Я подозреваю, что это тот же самый, что и теорема Фройда Митчелла.
Да. И, скорее всего, в одном даже тексте.
Да.
Да. Ну вот, там теорема про то, что если существуют произведения, проиндексированные набором даже стрелок, ну,
В этой категории?
да,
Угу.
то тогда эта категория – это предпорядок.
Угу.
Вот получается, условие, которое вы дали, оно, там мало категорий, в которых существуют все произведения.
Угу.
Но она, получается, удовлетворяет вот это условие теоремы, и значит, это предпорядок будет.
Да.
Вот, короче, понятно, что это, наверное, слишком длинный будет путь через вот это там.
Я не думаю, что слишком длинный путь, нормально вполне.
А это теорема по силам? Эту теорему по силам доказать?
Того самого Фрейда.
Да.
По-моему, по-английски он Фрид все-таки, но не важно. Но я на Лешу Кубанове тестировал, он у нее мгновенно доказал.
Кто это?
Это один из тут человек, который чаще всего выходит в доске.
ним 2 года уже учишься. Ладно,
Типа на одном курсе? В нашем вроде такого группе не было, да?
Ну, в смысле, они сами, да?
Да.
Даже кто придумал вот эти какие-то вещи, что там абелеву категории ничего не нужны?
Нет, это Сергей Давыдов. Он вообще не ходит сюда, насколько я помню.
Ну,
Он даже интеграл считает.
М?
Он вообще считает интегралы. Говорит, что это наука.
ну, просто как раз помню наоборот, последние годы очень много интересных работ именно про абелеву категории. Прям, я думаю, что с десяток я смогу найти, если подумаю.
Да, еще правда ли то, что каким-то образом теория категорий с физикой связана, оказывается?
Ну, само собой связано. Ну, в смысле, это в физике просто используется.
Ну, просто такое ощущение складывается, что в какой-то физике она как-то прям очень активно используется.
Рассказывай. То есть ты
Теорию струн, где А браны, это производная категория каких-то пучков.
Ну, это зеркальная симметрия, да. Ну, это Виттел придумал в 90-м или 91-м году, что если вы берете две суперструнные теории, у которых есть дополнительные еще измерения, как квантифицируются, например, мерные Кавабиявы комплексные, можно делать одним способом, можно сделать другим способом, а физическая теория как бы получается одна и та же, поэтому на самом деле данные из одного Кавабиява должны переходить в данные другого Кавабиява. С одной стороны, данные это производная категория кретных пучков, с другой стороны, данные это производная Фукаи, соответствующего Кавабиява. И вот гипотеза гомологической зеркальной симметрии, что они эквивалентны.
это гипотеза.
Но она доказана в каких-то, по-моему, в размерности 1 и 2 доказана, в размерности 3 я не слышал, но я просто уже давно не интересовался, что там происходит. Может быть, что-то, ну какие там уж частные случаи известны. Ну там какие-нибудь комбинаторные случаи должны быть известны, когда какие-нибудь полные пересечения вторических многообразий, что-нибудь от этого должно быть известно. Но это не, я бы не сказал, что это физика. Просто это вопрос тоже такой физика.
Физика — это интегралы.
Ну что, надо продолжить. So last time was an exercise that we haven't solved about the injective objects in the category of functors. Let me repeat the problem. So take injective objects in the category of all functors from A to abelian groups. So we assume that A is abelian category. Then this is contained in the right exact functors from A to the abelian groups. So in other words, any functor from A to abelian groups which is injective in this category is actually right exact.
So this is a set of, the category of additive functions from A to A, correct?
Yeah, this is the category for additive functors from A to abelian groups.
And we want to assume some injective objects in this category.
Mm-hmm. Mhm. No, I think if you change this to contravariant, that's still true. No, A is any category. You can replace A by the A opposite.
So just as a metric.
Yeah, you can. If you want, you can do this for contravariant. You sure? Okay.
Exact. We know that functor h y somehow turns it. So we have every sequence of functors stage. Because the functor is exact, so we have exact sequence of such functors.
Mm-hmm.
So then if I is injective, we have a sequence of and by Unid's lemma we have and there we have maps, it's natural. So we have and it is exact because this is exact.
Mm-hmm. Yeah, I think that's a correct solution.
Yeah, but how we obtain all this?
Well, this is given, right?
Yes.
So this is just the fact that the h with the lower object is the exact on the left. We know this. And this is just home into an injective object.
Yeah, how from the first to the second?
Uh,
What do we apply?
We just know that h with the lower object is the left exact, as well as the h with the upper object. These are two left exact functors.
They're different.
Yeah, different. Well, this is covariant version. If you want a contravariant version, you need to use different h with the upper object.
Like if we apply h that are applicable to this sequence, we will have exact, and for any object we have exact sequence, so we have exact sequence of functors.
Yeah, that might be true, but I wrote this formula so many times that I forget how to explain it. Yeah, so the next problem is not so easy, but it's, I think, useful in the applications. So here is the situation. You have two functors between two abelian categories, f and g, and these functors are adjoint. F is left adjoint, g is right adjoint, and we assume that A prime has enough injectives then the following two properties are equivalent. So G maps injective objects to injective objects. So let me write this in terms of formulas for shortness. Injectives of A prime, when I apply G, I'll get injectives of the A. Okay, so this is equivalent to the following, that F is exact. Yeah, show that these two properties are equivalent. Well, under these two assumptions, that you have adjoint functors and you have enough injectives in the A prime. Well, actually, in one direction, you don't even need this assumption. It's very straightforward. In the other direction, you need this. So one direction is easy. If you assume that F is exact, well, without any assumptions about enough injectives, you'll get this. The other direction is less trivial.
variables that doesn't need different coordinate objectives, right? The arrow
From the right to the left.
left.
Yeah. It's kind of easy observation.
Yeah.
We just need to write that the functors are adjoint, that's all. On the other direction, it's not so easy.
Yeah, there is like a sequence, but we want to derive from it that something is exact that lies inside holes.
Yeah. So take a sequence, right? Apply functor functor f to this sequence. So it will be exact on the right, because f is left adjoint. But on the left, it's not it's not immediately clear that it's exact. So I would say introduce some kernel. So say that there is a kernel, and then try to work with this kernel in terms what are maps from this kernel to any injective. What you can say about this? Mhm.
It's easy. And it's the same. So E is injective.
Yeah, but I would say it's a little bit differently, bro. It's the same argument. I just look at this isomorphism, which is just a homojunction between f and g, right? So I want to show that this functor is exact. But if f is exact and this is injective, this functor is exact, hence this functor is exact. So without writing explicitly short exact sequences. Yeah, sure.
Which two functors are f and the second one is hi?
And the second is, hi, yes.
So it's not like
Yeah, because I is injective. And our functor is just a composition of these two functors.
Okay, let's take and construct. Now, write something. No. Now, as E is injective, we can apply home factor to all these sequences. So we'll have something like sorry, this. And then we can see that there it's again the same thing as and I is injective. So this map is zero because g of I is injective and then we just apply the home factor to g I. Then this sequence with three terms is also. So this map is just zero.
Mm-hmm.
And so A of I is zero, but we take any injective I, and we know that there is some non-zero union because we have enough injectives.
Yeah, actually your proof is even shorter than what I have in mind.
Isn't actually obvious that all these isomorphisms, they agree with the maps that we have in short exact
Yeah, because this is unidous lemma and unidous lemma natural in both arguments.
Okay, so that
Yeah, unidous isomorphism. Well, not precise. Well, this is not unidous, this is just the adjunction, right? And by definition of the adjunction, this is natural in the first argument, natural in the second argument. That's the correct explanation.
so the explanation is natural of the conditions, right?
Yeah. Yeah, so now assume that A is abelian with enough injectives and projectives together. Then show that the following two conditions are equivalent. First condition, any sub-object of a projective object is projective. And second condition, any quotient of injective object is injective. You can also think, do you know examples of such categories?
What does it mean in objectives?
Well, for any object, non-zero object, there is an epimorphism from a projective object. Just a dual condition to having enough injectives. How about examples of such A's? Yeah, modules or principal ideal domain, that would be an example, yes. Now, in general, such categories are called hereditary categories, and if the module over some ring is satisfying these conditions, then the ring is called hereditary ring. Is it clear that actually you don't have to prove two directions? It's enough to show only one direction, because then you go to the opposite category and conditions 1 and 2 are interchanged. Well, in other words, if you have one proof, you immediately see the other proof, just reversing the arrows. They are both left exact. Not that you need to be accurate what you mean by a left exact, right? Because if this is contravariant function, the sequence you start with is exact on the right, and then it maps to the exact on the left. Yeah. So it looks like we're almost out of time, so maybe I just solve this problem.
Maybe confidence.
Mm,
I feel like I'm close, but I kind of need the final blow.
well,
Hey,
I can wait. I can wait.
We have like 15 minutes now.
Well, according to your clock, yes, but according to this clock, only 10. Yeah, if you have 15 minutes, sure, we can wait maybe another 10 minutes. Mm-hmm.
I'll try to prove that if we have every set object of projective is projected, then we get a condition. Okay, so first, well, let's say we have some injective object. We have some object inside it, and we get a quotient object, right? So we have a short exact sequence. Okay, I can write it like this. Right, so, and if we take just some object in the category, let's consider this function for like some arbitrary object right now. We will consider it for projective, but now let's consider it for arbitrary object. We know that this function is covariant and it's left exact. So if we have this short exact sequence, we get the following short exact sequence. That is we don't know if it's exact here, and
Mm-hmm.
for arbitrary it's not true. So, but how it's related to our task actually? Well, what we want to show in like is that well, if we have an exact sequence, this x says right now will be the same as here. Basics. We want to just apply the definition of the injective object for this. And the definition is that this function is exact, right?
Mm-hmm.
This sequence. So what does it mean? Well, it means that the following short exact sequence is exact. Well, since this is also left exact, we know that like 1, 0 we get automatically. We only need to show that the other one is 0, right? So we have this. It's a quadrivalent, so we have to switch
Mm-hmm.
everything. Right? Yeah, and we don't know yet, well, for arbitrary we can't know, but let's say there is the kernel of this map. Fine. Now what we want is we want to actually show that this kernel is 0, but and that would prove that this is injective, right? But
No,
now
so surjective.
subjective, yeah, but that would mean that this is exact, and it would
Yep.
prove that this object is injective.
Yep.
But actually, let's just consider not the arbitrary x, but the x that is projective.
Okay.
In case it was from phi. And well, x prime then is some sub-object of a projective object, so it's also projective, right?
Mm-hmm.
And well, now I guess everything is done, because then hx is exact for it. HP is exact, right? And well, it means. Oh, so let me. What do we have here? Oh yeah, sure. Wait, I forgot essential. We know that I is injective.
Mm-hmm.
So we can write just one sequence for free. This one. I forgot everywhere to write A again, I guess.
Sure. Well, actually, when you get some experience, you just write precisely like this. It's just parentheses, and it's understood what the category, in what category you're computing the homes.
So this is that sequence, and well, my point was that so I want to, yeah. So what I want is I want to understand these maps. Well, these maps are obvious; they're just composition with the canonical projection. But what I want is to understand that these things are just surjective. Because if it's surjective and here is 0, then here is also 0.
Yeah, but why this is surjective?
Well, but this is a surjective for not the arbitrary x, but for the projective. If I take x as a projective object. So it will be true for P, then the kernel is 0. That's true.
Wait, can you write what you're saying? That what you want to be surjective? The last arrow?
Well, here, well, I will write, yes. Well, I guess there is some also this one. Like that is
Yeah.
kernel of this.
Yeah.
Right? So now this sequence that is on the column
You're saying that if
is actually at the like this is explained. Yeah, actually like the logger like h logger x prime applied to this
sure.
short exact sequence, and it's exact if x prime is projected.
Yeah.
This is surjective. So well,
So
consider x to be
these two columns, the last two columns, are exact because you assume that the x is projective and x prime is also then projective. Sure. Then with this I agree.
Yeah, but then we get that this kernel is 0.
Yep. Under the assumption that x is projective.
Yeah. I didn't show that.
Yeah, and I think you still need to take any short exact sequence x prime, x and x double prime and see that the kernel is 0.
That's true. Well, so what I showed now is that if we take this projective, yeah, I guess
Yeah, you show that this is true for very special exact sequences, short exact sequences. Somehow you need to derive the general case for any short exact sequence that this is still true. And I don't think this is immediately clear.
yeah, it's not clear.
Ну, надо положить еще что-то положить прийти на верхнее что-то.
Мы не умеем вкладывать как-то перспективно. Мы умеем из перспективного что-то
Mhm.
Раз по-другому, то есть в этом, конечно, есть.
Yeah, and here you need to start with a short exact sequence, and then what you want to cover this by the
Oh, yeah.
short exact sequence, which with the projective.
I messed up.
Well, that might be possible, I think.
I just showed this. I mean, I saw this and then kind of tried to get the same kind of argument that we had in the previous.
No, at least my proof for this problem is different than the previous argument. In particular, I don't use these functors anywhere. I just work explicitly with short exact sequences. Yeah, well, maybe let's use this as another assignment problem. So if you have a solution, just give me the solution next time.
But this problem is not very hard, right?
No. I think it might be even easier than the previous problem. I think at least for me, it was easier than the previous problem.
The previous problem was kind of not so hard, but we needed to apply this functor to some big sequence, and that was not trivial.